A model can be accurate and still break common sense. XGBoost monotonic constraints force predictions to follow rules you already know should hold. This is the workflow you'll know how to run when we're done, which trains with monotone rules and predicts approvals that respect them. I'm Professor Pine, teaching AI foundations with simple Python. Imagine you build a loan risk model. You expect higher credit scores to lower risk. You expect higher loan-to-value to raise risk. But a powerful model can still flip those relationships in parts of the feature space. That creates compliance and trust issues. Monotonic constraints are a way to bake common sense into gradient-boosted trees, so the model never violates these plain rules. At its core, the idea is simple. Tell XGBoost which features must increase predictions and which must decrease them. Then, the training algorithm only considers trees that obey those directions. It trades a bit of raw fit for rule compliance. For a lender, that can mean fewer manual checks and more stable approvals. We will build a small, reproducible toy dataset that mimics credit score and loan-to-value. Then we train a baseline XGBoost regressor, count how often it breaks monotonic rules, and then retrain with constraints. Finally, we validate the final model across a grid to make sure the rules hold everywhere. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need to show where the problem lives and measure violations so the constraint payoff is clear. This snippet builds a small, reproducible loan risk dataset and counts where the monotonic rules are already broken. It seeds NumPy so everyone samples the same credit range and matching LTV draws. The synthetic risk is a combination. A linear drop of -0.08 per credit point, a 45 times loan-to-value penalty, some sinusoidal wiggles, and Gaussian noise to mimic underwriting quirks. Subtracting 45 times LTV isolates the credit effect, so np.diff flags any adjusted step that fails to fall. Sorting LTV and adding back 0.08 star credit mirrors the opposite adjustment to locate LTV violations. The printed counts give you a clear signal of how often simple domain rules are already being violated. That count motivates the constrained fit. Now train a plain XGBoost model and measure where it still misbehaves, so you can see the cost of ignoring rules. This example fits an unconstrained XGBRegressor baseline and checks how often it violates credit monotonicity. NumPy's column stack builds the feature matrix X from credit and LTV, while TTS creates a 25% holdout for validation. The alias XGBR makes an XGBRegressor with max depth equals 5, so trees are expressive enough to capture bumps without going wild. After fitting model on XTR and predicting YTE, we compute RMSE to see raw accuracy when rules are ignored. Then, a probe grid fixes LTV at 0.55 and sweeps credit upward. np.diff on those predictions counts how often the unconstrained model perversely increases risk as credit improves. We saw the problem and the unconstrained model's accuracy. Next, force the business logic into the learner and compare. This code applies monotone constraints, so XGBRegressor must respect the decreasing credit and increasing LTV business rules. Defining mono as -1,1 maps credit first and LTV second, forcing credit to decrease predictions and LTV to increase them. The constrained model reuses the original train split and keeps max depth equals 5. So the only change is passing monotone constraints into XGBR. RMSE now comes from constrained.predictXTE and shows the modest price paid for rule compliance. The credit fix count repeats the probe sweep and should drop to 0, while LTV breaks inspects the LTV probe sweep to confirm the constrained estimator never rewards higher collateral ratios with lower risk. Monotone constraints work, but tree builders and training schedules matter for stability. We tune the booster to use the histogram method and a longer, gentler learning schedule, so constraints have ample split candidates. This snippet retunes the constrained learner to use the hist tree method and stabilizes training with early stopping. XGBR now receives tree method equals hist, so it builds splits from histograms, and max bin equals 256 keeps enough candidate thresholds for the monotone constraints to operate. Setting learning rate equals 0.05 with n estimators equals 800 stretches the boosting schedule, and early stopping rounds equals 20 on the shared eval set stops training once validation RMSE plateaus. HistModel.fit reuses XTR and YTR, silences extra logging via verbose false, and preserves evaluation history for inspection. Best score captures the best validation RMSE, and recomputing credit OK plus LTV OK with NP diff on the probe and LTV probe confirms both monotone directions hold under the tuned regimen. Before deploying, test the model thoroughly across the whole input space to ensure no local violations hide in corners. A dense grid sweep will catch any surprises. This example sweeps a dense credit LTV grid through hist model to confirm global monotonic behavior before deployment. Grid credit and grid LTV define the evaluation lattice, and np.meshgrid returns CM and LM, so every credit LTV pair appears once. NP column stack flattens that mesh for hist model predict, which we then reshape back into a matrix whose rows are credit and columns are LTV. NP diff along axis 0 checks that risk never rises as credit improves, while the axis 1 check verifies higher LTV never lowers risk. The printed booleans and average risk summarize that the final model is globally rule-abiding. This mapping shows you how a toy proof maps to a real pipeline. Replace the toy features with your production fields, keep the same monotone mapping, and run the grid sweep on representative ranges before releasing the model. Recap. Monotonic constraints tell XGBoost to honor the directional rules you already trust. Use them when domain logic must not be violated. Credit scoring and pricing are common examples. The trade-off is a small hit to raw fit, so measure that gap and decide if the stability is worth it. Next step, tune the learning rate and the number of estimators in the hist model to balance validation RMSE and strict rule adherence. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.